Section 14.3, partial derivatives. Notice this is not the same as total derivative for single value functions. Because the function involves multi-variables, so therefore we cannot call it derivative. We have to call it partial derivative. And you will see in a minute why it's partial. Recall the definition of derivative for single value function was f prime of x, limit of when you increment x by the amount of h, f of x plus h minus f of x divided by h as h approaches to 0. As a matter of fact, this is the slope of the secant line when you connect two distinct points on the curve and let the distance between them gets closer and closer to 0. However, for function of two variables, namely like z is equal to fxy, the partial derivative with respect to x is denoted by this notation. Notice instead of using d, we use curve d, so kind of like curve it. So this represents partial derivative of f with respect to x. Sometimes there are other notations like f subscript x, or z subscript x, or partial of z with respect to x. Remember, z is the same as fxy. But by definition, the partial derivative of f with respect to x is the limit of f of x plus h y minus f of xy over h. By definition, notice the y's pretty much stays the same. So what does that mean? That means when we take the partial derivative of a two-variable function, we keep the y's constant. Similarly, when you take the partial derivative of same function with respect to y, you keep what? X is constant. Notice x's do not change. Do you see it? Still the same x. The only thing we do is increment the y, not x's. So with that in mind, let's take a look at this example. What would be the partial derivative of f with respect to x and partial derivative of y with respect to x if f of xy is 4x squared minus 2y plus 7x to the 4y to the 5th? Keep in mind, these are the notations, so choose your favorite notation. Make sure whatever you do not use d. This is curve d, yes? Or use the subscript notation. So partial derivative of f with respect to x, we're going to pretend these y's are constant. So what's going to happen is we're going to take the derivative of this guy, that's 8x. This guy is constant, so derivative of constant is 0. You don't see it. But here, this guy, this is constant because it's the coefficient of 7x to the 4. So what you do, you take the derivative of 7x to the 4, which is 28x cubed, and this guy goes for the right. In other words, in this term, since y was all by itself and we're keeping the y's constant, derivative is 0. However, here, y is the coefficient of 7x to the 4, so it goes for the right. Okay, just like 7 goes for the right when you take the derivative of x to the 4, okay, which is 4x to the 3rd, but 4 times 7 is 28. On the other hand, when you have partial derivative of f with respect to y, notice we keep the x's constant. So if the x term appears all by itself, like this guy, it's 0. But if it is coefficient of a y term, then it goes for the right. So in this case, what we have is what? Is this guy is 0. You know, we're taking the partial derivative with respect to y, so x's are constant, so this guy is 0. Derivative of this with respect to y is -2. But derivative of the last term, the derivative of y to the 5th is 5y to the 4, but 7x to the 4 goes for the right, and you get what? 35x to the 4, y to the 4. And this would be like partial derivative of f with respect to y. Sometimes the y happens to be part of the argument of a trig function, so you have to be very careful how to evaluate these guys. To find the partial derivative of f with respect to x, I need to use product rule. Derivative of this guy with respect to x is 2x times cosine of xy, plus derivative of this guy, which is minus sine of xy, times the partial derivative of what? Of xy with respect to what? X. So that means y is constant, so that guy goes for the right. Do you see it? So the partial derivative of xy is just y. Pretend this is like derivative of 4x. Pretend y is 4, so 4 goes for the right. Evaluating this at this given point, 1/2 comma pi, that's x, that's your y, the answer would be negative pi. On the other hand, for partial derivative of f with respect to y, we're going to keep the x's constant. Because x squared has been multiplied by cosine of xy, so it goes for the right. It acts like a coefficient. All you have to do is take the partial derivative of this cosine of xy with respect to y. So x squared goes for the right. Partial derivative of cosine is minus sine xy, correct? Times partial derivative of xy with respect to y. So x acts like a coefficient and it goes for the right. Evaluating this at 1/2 comma pi, that's your x, that's your y, you get negative 1/8. What is the geometric interpretation of partial derivative? Partial derivative, like let's say you have a surface like this guy, which is upside down, what? Elliptic paraboloid, correct? Because if this was z is equal to x squared plus 2y squared, it would be a paraboloid opening along the what? Z-axis. Because it's negative, so it goes upside down, and because you have a 4, so you got to shift it 4 units up. So let's say we like to find partial derivative of what? F with respect to x at point 1 comma 1. Excuse me. So how would you do this? What we have to do is take the intersection of what? The surface, what? Z is equal to 4 minus x squared minus 2y squared, and z is equal to, y is equal to 1. Remember, we're going to keep the y's constant. So at point, what was it? 1, 1. So y is constant. Remember, this is a surface, correct? This is a plane. Y is equal to constant is a plane. So here is y is equal to 1. So that's a plane, which is y is equal to 1. And here is the what? Elliptic paraboloid, which opens upwards, and it has been shifted 4 units along the z-axis. Guess what? The intersection of this plane and this surface is a curve. So we're going to call that curve C. Do you see it? So curve C, or C1 as I call it, is intersection of the surface with the vertical plane y is equal to 1. Think of it as the trace of the surface in the plane y is equal to 1. So at point 1, 1, excuse me, so if you stick 1, 1 here for x and y, z becomes 1 as well. So at that point, when you draw this tangent line, this partial derivative gives you the slope of the tangent line at point P to the curve C1 in the positive x-axis direction. Okay. Similarly, this guy, partial derivative of f with respect to y, would be the intersection of z is equal to 4 minus x squared minus 2y squared with x equals 1, which is a vertical what? Plane parallel to the yz axis. Okay, so at the point of intersection, the intersection of these two surfaces is a curve, just like what we had previously. And at that particular point, if you draw the tangent line, so what you're finding is the slope of the tangent line at point P to curve C2, which I don't have a picture here. That's intersection of the surface with the vertical plane, what, x equals 1 in positive y direction. So in practical problems, partial derivative of f with respect to x represents rate of change of surface in positive x direction, and partial derivative of y with f with respect to y represents the rate of change, how fast the surface is changing in positive y direction. So partial derivative of f with respect to x, rate of change in positive x-axis, partial derivative of f with respect to y, rate of change of the surface in positive y direction. So we have, just like we had first derivative, second derivative, here we say first order partial derivative. And these are the notations for partial derivative of f with respect to x. Any of these notations are legit to use. Then we have second order partial derivatives. So that reads second partial derivative of f with respect to x. In terms of subscript, you can use fxx, right? Partial derivative of f with respect to y twice, that's fyy. Then we have mixed second order partial derivative. These are mixed partials, and they kind of go like this. Partial derivative, second partial derivative of y, then with respect to x. So that's like fyx. So what you do, you take the partial derivative of f with respect to y, whatever the answer you come up with, then you take the partial derivative of that guy with respect to x. So the next one is partial derivative of what? F with respect to x first, y second. So these are called mixed partials. According to the gentleman mathematician Clairaut, the partial derivatives, they are always equal. So mixed partial derivatives, they are always, rain or shine, equal. Mr. Clairaut has proven that. Then you have like third order partials, you know, fxx, fyy. Then you have third order mixed partials, fxyy. I don't know, fxxy, and it goes. So the idea is as follows. Suppose fxy is equal to 2x minus y to the power of 5. Find zxx, zxy, zxyx. Zxx is second order partial derivative. So you got to take the partial derivative of this twice, both sides with respect to x. First time around, you take the partial derivative, you get 5 times 2x minus y to the power of 4 times partial derivative of the base with respect to x. So y is constant, so you just get 2, because that's all you have to take the derivative of, the 2x. So you get this. Now to find zxx, you take the partial derivative of part A one more time with respect to x. So that would be 10 times 4, which is 40, 2x minus y to the third power. Don't forget, partial derivative of 2x minus y is 2. So you get 80 times 2x minus y cubed. Now, this is a mixed partial, which is what? Zxy. So what do? You go back to part A, which is partial derivative of x. Take partial derivative of the answer in part A with respect to y. So what happens, that's like 10 times 4 is 40, 2x minus y to the third power. Partial derivative of this guy with respect to y is -1, correct? So you get -40, 2x minus y cubed. However, if I was, remember this is a mixed partial, so the question is, what is zy? That's like partial derivative of this guy with respect to y is 5 times 2x minus y to the power of what? 4 times -1. So that's -5, 2x minus y to the 4. And now let's take the partial derivative of what? Second partial derivative of what? Y with respect to x. In other words, I'm trying to see if these two answers, if I switch the order of mixed partials, are going to come up the same. So I already got the partial with respect to y, correct? So now I'm going to take the partial of this guy with respect to x. So that's going to be like, let's say, okay, let's see now. That's going to be negative, what, 20 times 2x minus y cubed times partial derivative of 2x minus y with respect to x, which is 2. So you get negative 40, 2x minus y cubed. Notice the mixed partials, they always come up the same according to Mr. Clairaut's theorem. Sometimes you may have to take implicit differentiation. In other words, there is no way you can solve the equation for z. So what happens, you get this kind of function, fxyz is equal to constant. So those are called implicit functions. So we have to use implicit differentiation, such as this guy. So the question is, given y times z is equal to natural log of x plus c, can you find partial of z with respect to x, partial of z with respect to y? Notice there is no way I can solve this for z. So I have to take the derivative as I see the expression from left to right. So partial derivative of z with respect to x. So this guy acts like a constant because we keep the y's constant. So that goes for the right. And I have to use what? That as a coefficient. But then I have to take partial derivative of z with respect to x. So this guy acts like a coefficient when you take in partial derivative of z with respect to x, because remember, we're keeping what? Y's constant, correct? On the right side, the derivative of a natural log is 1 over the logorand. But then remember, I'm taking the partial derivative of this guy with respect to x. So the partial derivative of x is 1. Partial derivative of z with respect to x is, dz dx. Somehow you have to manipulate this equation and isolate what the equation for dz dx. Turns out the answer is 1 over y times x plus c minus 1. On the other hand, if the idea was find the partial derivative of z with respect to y, so we need to keep x as constant. So here, what happens is we get what? We use product rule, because now we take in the partial derivative with respect to y, so y is a variable. So derivative of y with respect to y is 1 times z, plus partial derivative of what? Z with respect to y is dz dy times y. So here I have to use so-called product rule, okay? On the right side, derivative of natural log is 1 over logorand times partial derivative of this guy with respect to y. So x is constant. So the derivative of constant is 0, but you still have to take partial derivative of z with respect to y. Once you get to this point, now what you have to do is try to manipulate the equation and isolate what? The equation for partial derivative of y with z with respect to y, and turns out this would be the answer. Okay. Some of the application of what? Second order partial derivative, it shows up in fields like, when you're dealing with harmonic functions, heat conductions, fluid flow, electric potential. Notice the equation is uxx plus uyy is equal to 0. On the other hand, sometimes you have utt, that's like second partial of u with respect to t, a squared uxx, this a squared is constant. Believe it or not, that's the wave equation. So when we refer to wave, we're talking about ocean, sound, or light waves. So these are few examples of why do we have to take second partial derivative. okay, because they show up in real life and they show up mostly in engineering and what? Physics classes. And that pretty much concludes this section. Thank you.